All right, hello and welcome to week 2, lecture 3, I assume. We're going to continue our slides for logic and hopefully finish them and start some new ones this week. At least that's the plan. So we ended last time talking about quantifiers, or getting ready to talk about quantifiers. We first talked about predicates, and that's where we stopped. So a predicate, it's just a logical function in a sense. It takes some variables, and you can put whatever you want in them, and sometimes it's true, sometimes it's false, depending on those variables, right? It's just a function from some domain to true and false. Okay? So with that in mind, let's now learn some new symbols. Fun, fun. So the first one's called a universal quantifier. So we'd like to say stuff about the domain of a predicate. Okay? If we go back to here, dun dun dun. The domain is just the set of all possible values for a variable, and we'd like to say something like p of x is true no matter what x is. Okay? I should add the word is. Or alternatively, this is equivalent. P of x is true for every x. P of x is true for all x, we say. Okay? So we use this upside down A symbol to mean for all. Okay? So whenever you see flipped A, it means for all. Okay? Just read it like that. So, with an example now, if we define p of x to be Lawton loves x, and the domain of p is all cats, then obviously, for all x, p of x, this entire statement is true, okay? So, if we translate this to English, it's saying, for all cats, Lawton loves that cat, okay? Lawton loves every cat in the world. That's the one. All right, so x, we say, ranges over every cat in the domain, okay? So the idea is this for all sign, it needs a variable after it, and it introduces that variable. It's a brand new one, and you can use it for the rest of the statement. So when you say for all y or something, you can use y here now as much as you want. Y can appear as much as you want. As often as you would like. So that's the idea. For all introduces a new variable, and you can use it in the rest of the statement, and it is, we say, quantified universally. And the name of the variable doesn't actually matter. So you could say for all y, p of y, and this would be the same as for all x, p of x, because it's just you change the name of the variable. So it's like, okay, for every cat called y, Lawton loves that cat y. For every cat called z, Lawton loves that cat, okay? So take every cat in the world and give him a chance at being y. P of y is true for that cat, okay? And on and on and on, forever and ever and ever. So the variable name doesn't matter, and that is the idea. Okay, so on the flip side, you have a dual of the universal quantifier called the existential quantifier. So kind of like existential dread, right? So sometimes we don't want to commit to all of something. That's a little too much. We don't like that. So sometimes we'd like to say things like, p of x is true, yeah, but only sometimes, for at least one x value, okay? There exists an x such that p of x is true for that x. Okay, so we use the backwards e in the opposite axis to mean there exists. Okay, so whenever you see this, you read it as there exists. Okay? And another similar example, if p of x is defined as Lawton owns an x, and the domain of p is all cars, then I don't own every car in the world, but I own one car. Okay? So there exists an x such that p of x is true. This entire statement is one big statement in logic. And you can translate it to English as there is a car that Lawton owns. Lawton owns at least one car. That's the idea. Okay, there exists an x. One of the cars in the world, call it x. It happens to be mine. Okay? Hopefully this is making sense. I know it's very abstract. We're going to get to an example in a second. So yeah, I just own one car. It's not true that for all of x, p of x is true for this one. That's not true, because I don't own every car in the world. That would be weird. Okay? That's the idea. And again, the existential quantifier introduces a new variable so that you can use it for the rest of your statement. So you have for all z, and z can now appear as much as you want over here. Okay, so it just means that for one thing in the domain, whatever is after this quantifier we're claiming is true. Okay, so again, you can change the variable as long as you're consistent. There's no difference between saying that there exists a car called Y such that P of Y is true, and there exists a car called Z such that P of Z is true. It's saying the exact same thing. Okay, so it's just like when you write a function in C++. It makes no difference the name of your variable so long as you use it the same way. Okay, or the name of your parameter. All right, so finally an example to make this make some sense. So let's define two predicates, P and Q, and the domain is the set of all students in the class. So whenever we introduce a variable for these predicates, so that variable ranges over all the students in this class. All right, so P of X, we'll define that to mean X was born in September, and Q of X to mean that X is at least 20 years old. Okay, so I want you to take a guess as to the true or false values of these two statements. So maybe pause for a second, think about the first one. Do you think it's true that for all of X, P of X? And assuming that you're back now, what does this really mean in English? It's saying something like, for every student in the class, P of X is true for all of them. Okay, give me an arbitrary student X, pick one out of the class. We're saying that P of X is true. And I can do this for every student in the class. All right, so this is saying that every student in the class was born in September. And I'm pretty sure that it's not true. Okay, that would be a very interesting statement. If that were true, that would be fun though. Okay, how about there exists a Z such that not Q of Z is true? So think about this for a second. We're saying that there is some person in the class, some Z, call them Z, such that not Q of Z is true for that person. Okay, so if we translate that even further to English, what do you think that means? Maybe take a second to think about it. What it's saying is there is a student for which this is not true. There's a student that is under 20 years old. At least one. Okay, that's the idea. So there exists some student, call him Z, such that not Q of Z is true for that student. Okay, it's not true that they're 20 years old. Okay, hopefully this is all coming together, and I think this is probably true. When I took my equivalent of CSCI 26 at Fresno State, I was, I think, 19, either 18 or 19. So there we go. All right. So hopefully this is now making more sense that we're using this in an example. Let's keep on going. Let's have another. All right, so take a second to think about this question. The domain now is A, B, and C for both P and Q, okay? So for these predicates P and Q that I'm defining in this table down here, the table is going to show the value of the predicates for each of the elements in the domain. So this is, so right here, for example, it's saying that P of A equals true. Q of B equals true. Okay, that's the idea. And so the domain of these things, of these predicates, are just A, B, and C. That's all they could range over. So now it's quite easy to look at for all X, and there exists a Y. I'll show you the trick. All right, so take a second to think about, is it true that for all X, not P of X is true? Okay, so what would have to be true for this to be the case? Well, for all X just means try P of X on every possible element of the domain. Well, we got 3. Let's just do all 3. We'll look at P of A, we'll look at P of B, and we'll look at P of C. And this is claiming that not P of A is true, and not P of B is true, and not P of C is true. Do you see how the for all is essentially a bunch of ands? Okay, that's the key idea. For all is a bunch of ands. Okay, so is it true now that for all x not p of x is true? Well, is this newer statement, this more easy to think about statement, true? Is it true that it's not true? I keep on saying true. This is really hard to explain and not keep on saying the same words, sorry. So, is it true that all of these are false, is the idea. It's not true that all of these are true. Okay? So, equivalently, is it false? Is p of x false for every possible x? No. I've got two examples where they're true. Okay? So this is false. Hopefully you followed that, sorry. I'll get better as the semester progresses with saying other words than true and false. Let's see. Okay, let's try B now. So, is it true that there exists a y such that not q of y is true? And again, exists just means there's at least one element in the domain of q, which is a, b, and c, such that this statement is true for that element. And this translates to, if you think about it, well, maybe it's a. Maybe not q of a is true. But for this to happen, for this to be true, at least one element of the domain must hold, not q of y, must hold for it. So if it's not that one, it must be another one. Or not q of b. Or not q of c. Hopefully that's making sense. So the key idea here is there exists is just a bunch of ors. You got to find one thing, one y, to make this true. Okay, let's put some apostrophes just so that we don't get confused. So I think you'll find that this is in fact true because we have a witness to this fact. Q of c is false. Because Q of c is false, which is also written as this, not Q of c is true. That's the idea. Okay, so hopefully that's making some more sense now. For all x not p of x, it's just, okay, try every element in the domain, make sure that p of x is false. Exists a y such that not q of y is true? Well, you need to find one y in the domain such that for that particular y, q of y is false. Okay? That is where we're going. All right, so if that wasn't confusing enough, we're now going to negate quantified statements. Okay, so because these are secretly a bunch of ors or a bunch of ands, we can also secretly use De Morgan's rules. Okay, so De Morgan's law goes even further, and we're going to figure out how to push this negation inwards in a universally quantified statement and an existentially quantified statement. Okay, so let's reason about this in English. So if I claim that not all of this is true, it's not true that for all of x, p of x, maybe I should put these in parentheses just to make it very clear what's going on. This is saying that it's not true that for all of x, p of x. Okay? If you think about this long enough, it means that there must be one element of the domain where p of x isn't true, because that would cause this to be false. It's not true that all of them are true, so at least one must be false. Okay? That's the idea. So what we can do, just like ands get flipped to ors, for alls get flipped to there exists. Okay? This is a really cool concept, and it's culminating in all that we've learned so far. Okay. So, if you negate a universally quantified statement, you just bring the negation inwards and flip the for all to there exists. Okay? So we get now there exists an x such that not p of x is true. That's the opposite. That's the excuse me, that's the negation of it's not true that for all of x, p of x is true. There must be one x such that it's false. Okay, hopefully that's making some sense. And likewise, for it's not true that there exists an x such that q of x, well, that means that we can't find even one. We can't find even one x in the domain such that q of x is true. That means it must be false for all of them. You see that? So the ors get flipped to ands now. So we can now push this negation inward by putting it there and then swapping the there exists with a for all. So it's not true that there is a q of x that's true for some x in the domain. That means that it must be false for all of them. Okay? For all x, it's not q of x holds. Okay? And again, I know this is getting very, very vague, probably, because we're using variables, but there is some light at the end of the tunnel. There will be more examples, I promise. And when you read about this in your book, they might use better words. Okay, so let's talk about proving things now, because the whole point of logic is to go and say, hey, this thing that I want to prove, it's true. And here's why. All right, so let's get started with proving some stuff. So we're going to work our way up to it, slowly but surely, and I'll just give you a taste of what it's like at the beginning here. So I want you to imagine when you prove a for all statement or a there exists statement, or both, it's like a fight, okay? So you're fighting with your worst enemy, and the fight is over who gets to pick the values of the variables. Okay, so with for all, it's your worst enemy that always gets to pick. Okay, they get to pick the variable's value and try and make the predicate false. So like if you're trying to prove for all x p of x, your enemy is going to throw at you the worst element of the domain, and you have to go and prove p of x is true for that element. Okay, so those are the breaks, and it's unfortunate. For all is a lot harder usually to prove than there exists. Okay, with there exists though, you have the other side of the coin. You get to pick the value of the variable, and you get to try and make the predicate true. Because to prove there exists an x such that p of x, you just have to find one good element. You can pick the best element in the domain, the one that's easiest to prove this statement for. Okay, and you get to use your weapon of choice, whatever you want. Your enemy can't say anything because you only have to find one thing, whereas for this one you have to prove for everything. And your enemy's going to throw hard stuff at you. Okay, so that's when you have a single there all or a single there exists. But this does scale to multiple quantifiers, because maybe you have like for all x there exists a y such that for all z there exists a p such that blah 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 blah. Okay, and when you have this kind of situation with multiple quantifiers, you always are going to work your way from left to right. You're going to work on picking a value for this one, picking a value for that one, picking a value for this one, and remembering that eventually you're going to have to range over all the things when it's a for all. But you can worry about that later. Okay, so what you do is you can imagine it this way, having to prove it. You're just going back and forth with your worst enemy again. If you're trying to prove a for all, that's the current variable you're on, your enemy gets to pick, and then you get to prove the rest of the statement. You work your way down. If it's a there exists, maybe you're here, you get to pick the value for y, and then you can work on proving the rest of the statement. Okay, so that's how you pick the variables, and that's how you can prove things. Essentially, we're going to get to the real way to do it in just a little bit. But I also want to show you and give some more examples of when you double up on quantifiers of the same type, the order doesn't usually matter for those variables, which is really nice. You can move them around. The x and the y here don't really matter. So this statement, I want you to read it and hopefully understand it. So take a second to think about what you think this statement means. Assuming like the domain of the x and y is just any number. So this is saying, so for every x and for every y, it's true that either x plus y is less than or equal to x, or x plus y is greater than or equal to x. And this is always true. This is actually a true statement, because no matter what values you pick, either y is positive or negative, and that'll cause one of these two to be true. If it's 0, it'll cause both of them to be true. Okay. And so if we were to swap y and x, it doesn't really matter, because this is just saying, okay, yeah, for every y, for every x, it's true that this is true. Okay? So the order of picking doesn't really matter, because your worst enemy gets to go twice, right? And same for there exists, because you get to go twice. It's not a big deal, most of the time. But when you have different kinds of quantifiers, the order, unfortunately, almost always matters. And there's a huge difference between these two, and you cannot rearrange things. Okay, let me prove that to you. So let's define the predicate m of xy, to mean that X sent a cat meme to Y, where the domain of X and Y is like people. So like M of Lawton, I sent a cat meme to my cat, let's say. That's the kind of statement you can have. And X and Y just range over everybody. People, or beings that have life, or something, who knows. So let me prove to you that for all, and there exists, don't really matter in terms of order, at least for this predicate. So here's how you can read, this is a good example of translation again. Here's how you can read this statement in English. It's saying that everyone sent a cat meme to everyone. And let's see why. So X is going to range over the senders, Y is going to range over the receivers, and it's saying that, all right, no matter who, like try everybody, everybody gets to be a sender, everybody gets to be a receiver, and this is true for that, for all of them, okay? M of XY is true for every possible X and Y. Everyone sent a cat meme to everyone else, okay? Or everyone. Hopefully that makes sense, and hopefully you can see why this swapping these doesn't really matter, because it's like, okay, yeah, we'll pick the sender first instead of the receiver, or we'll pick the receiver first instead of the sender. That's the idea. So that's for all, and there exists is essentially the same. Let's talk about this one. So to translate this statement to English, I hope that you can see that it's saying someone sent a cat meme to someone, because we get to pick the sender, just one, and you get to pick a receiver, just one. So there is one X, there's one Y, such that this is true. M of XY. Someone sent a cat meme to someone. At least one person sent a cat meme to one other person. That's the idea. Okay, and again, you can swap these because it's like, okay, we'll just pick, we know that Lawton sent a cat meme to Lonzo, we'll just pick Lonzo first instead of Lawton, because we'll pick the receiver before the sender now. Not a big deal. Now, let me show you about how unfortunate it is that these two are a big deal. You cannot swap them. Okay, so let's look at this first statement. For all X, there exists a Y such that MXY is true. Okay, and this is where the order really matters. You pick, your enemy gets to pick, and then you prove the rest. Or you pick, and then you get to prove the rest. Let's talk about this. So the idea is your enemy gets to pick. For all X, there exists a Y such that M of XY is true. Okay, so what this is saying is everyone sent a cat meme to someone, because first you pick the people, you pick a sender, and then you have to show that there is some Y. Your enemy picks the sender, and then you have to show that there's some Y that the sender sent a cat meme to. Okay? Hopefully you can read it in that order. First the enemy picks the sender, then you get to pick who received the cat meme from that sender. Okay, because you're having to show this inner statement. Okay, this is saying that everyone sent a cat meme to someone, because first, like X ranges over all the people, and then all the senders, and then there's at least one person that received a value from that particular sender. Okay, hopefully that's making some sense. Please come to office hours, please yell at me if it's not. This is what I want to get through to you. Let's try the other option and see why it's different. This is a bit opposite. It's saying that someone sent a cat meme to everyone. Okay, and I hope you see why. So first, you get to pick the someone. You get to pick one person who is sending, the sender, so that X remains the same for the rest of this statement, because you have to now go and prove for all Y, M of XY. You have decided your X. Now it's your enemy's turn to pick the Y, and you got to try all of them. Okay? So you first fix the X, fix one sender, and then you have to show for all Y, M of XY is true. For every other person, for every person, that X sent a cat meme to that person. Okay? So if you pick me, like I'm the X, you have to show that for all of Y, for every other person, M of Lawton Y, I particularly sent a cat meme to everyone else. You have less choice in the matter than this statement. Okay? Because you can pick a different Y for each X because of the order in which these things occur. Okay? That is the key difference. You always go from left to right in terms of quantifiers, and when they are different kinds, it can be easier or harder to prove something. Okay? I think that this one maybe is probably easier to prove than this one, given the set of people. Okay, so let's make this even more concrete now, because it might still be fuzzy, and that's okay. Let me define this predicate, p of xy, to be xy equals 1, and x and y can range over all positive numbers, so it can't be 0, can't be negative. So here are some examples of p, such that p of xy is true. So p1 is totally true, because 1 times 1 is 1. p1/2 and 2 is true, because 1/2 times 2 is 1. So now let's try and prove this one, or let's at least think about it. So is it true that for all x, there exists a y such that p of xy is true? So again, remember the order. Your worst enemy is going to pick an x, and he's going to pick all of them eventually. What's the worst possible x you can pick? There actually probably isn't one. So say your enemy picks, I don't know, 1/2. You now have to counter that. You have to say that there exists a y such that p of xy is true for this particular x that your enemy chose. You didn't have a say in the matter. Now you get to pick your best y to hopefully prove that this is true. And yes, you can totally pick your y. In fact, dun dun dun, you can always do it for this particular domain, because it can't be 0. No matter what your enemy picks first for x, like, I don't know, 72/34, you can always counter with, yeah, there's totally a y. There's at least one. It's the reciprocal that makes this predicate true. Ooh, yes. So this is a true statement. You get to pick a different y, though, for each x because of the order. Your enemy goes first, then you go. Okay? That is the idea, and that's why it's important. Now, we have the other side of the coin. And this is a bit different because the x is existentially quantified and the y is universally quantified. So is it true that there exists some x such that for all y, p of xy is true? So you first have to fix an x and then show that for all y, p of that x and y is true. So for example, you get to pick your best one. You get to show, like, okay, my best possible x is 24. And now you have to show, after fixing that x equals 24, you now have to show for all possible y's, like for 2, p of 24, and 3, it's always true that xy equals 1. And that is going to be impossible, because it's not true that there is just one x that for all y, no matter what you multiply by, xy is 1. That makes no sense at all. Okay, maybe if it was xy equals 0, that's possible, because then you can choose x being 0. But this does not work. This is false. This is a false statement, and I hope you see it, because there is not just one x that you can pick that multiplies with every other y to get 1. Okay? So you get to pick an x first, and then your enemy gets to hit it with any value they want. So you got to pick just one x. You are forced to pick just one x, and then your enemy gets a go. Gets to try every possible values, even the bad ones. Okay? Your x had better work for every possible y. Okay? I hope you see that the order sucks in this case. So this is kind of a concept that will come up later. It's a lot easier to prove a for all there exists than it is to prove an exists for all, because you have the home team advantage. You get to go second. You get to pick a different value for each thing that your enemy picks. Okay? So that's a lot harder than having to pick first and then counter everything with that one ultimate weapon. Okay? So again, hopefully slowly but surely, these ideas are getting clearer in your mind, and that's all I want. Okay? You'll get a lot more examples in your book and in your homework. But let's keep going. Let's move on now to another nice example. This one's for you, so take a second to pause the video and figure out the answer to this. So here's a predicate p. The domain is all the pairs of integers, so x and y are both integers. Okay? And we get to define it as, okay, p of xy is saying that x plus y equals 2. It's asserting that x plus y is 2. Okay? So things like p of 1, 1, yes, that's true. P of 0, 2 is true. And I want you to think about this one. Is it true that there exists an x such that for all y, p of xy is true. So pause the video, think about that, and come back. So remember, this is the hard way, okay? This is the hard way. So what it is, it's probably no. What it's doing is you have to pick one good x such that for all y, for any y that your enemy could pick, p of xy is true, x plus y is 2. And it's impossible, because the second you fix an x, like, okay, I have chosen my x, it is 1. And I have to pick, now I have to counter anything that my enemy could give me. The enemy could totally give me 42, and then it doesn't work, okay? So it is not true that for every, there exists an x such that for all y, x plus y is 2, okay? Hopefully you can see that. That is impossible to happen just using math rules. Now, let's try the flip side. Is it true that for all x, there exists a y such that p of yx is true? And so what this is saying is, okay, your enemy gets to pick an x, so it's been chosen. Let's keep it a variable, call it x. We have to show, because x is going to range over everything anyway, we have to show that there's one good y for that particular x, such that p of yx holds. Oh, sorry, I think I did it backwards. Yeah, I just want... It doesn't matter because addition is a commutative, but it should have been p of xy, sorry. So think about this one, and maybe come back. So for whatever x that your enemy chooses, you have to find one good y. You have to prove that there exists a y for that x, such that x plus y is 2. And let me show you how you could find that y. Y equals 2 minus x. Okay? So this is true because for every x that your enemy chooses, whatever that x value is, we can pick a y, a different y each time, which is really nice, and just make it 2 minus x. And suddenly, you have a value, okay? Because then y plus x will be exactly 2. So this one's true, yes. It is true that for all x, there exists a y such that p of xy is true. Okay, so hopefully you can see it. It's getting even less fuzzy. And yeah, we're just going to give more examples like this until you get it. So this was all very hand-wavy in terms of how we actually proved things. And I want to come up with like the real way of doing it now. I want to teach you how to reason logically, not just saying, oh yes, this makes sense because of math. Like, no, giving real reasons why, yes, for all x, there exists a y such that p of xy is true. And this is the exact reason, okay? So let us reason with logic. Let's prove new things from old things. So let's talk about what it means to reason logically. You have a bunch of new terms now. You're trying to prove something. That is your argument. You have an argument that you're making. It's just a sequence of propositions. Those are your hypotheses. So you assume these things, and then you want a final proposition to be true based on these hypotheses. That is called the conclusion. Okay? So that is your argument. So here's an example argument. I'm going to assume, these are my hypotheses, and this is my conclusion. I'm going to assume P, and I'm going to assume P implies Q, and then I want to prove these three dots. If you've never seen them before, they just mean therefore. Then I want to prove Q is true, okay, based on these assumptions. Sometimes people put a line here. You'll see it with and without it in the book, and so I will try and use both in these slides just to make it clearer. Okay, so that's an argument. You're trying to prove something. This is what you want. This is what you assume you get to have. And you have to go off and use the rules of logic to prove Q. And so let me show you how to do that. So an argument is valid, like it makes sense and it is true, if the conclusion is true whenever the hypotheses are all true. Because we're trying to assume these hypotheses are true, and then we're trying to use them to prove that Q is true. Okay, the conclusion is true. And so a good argument is one that is valid. If it's true that the hypotheses are true, then you can always prove that the conclusion is true. Okay, and that's a valid argument. And then if none of that holds, if one thing doesn't hold, then it's invalid. Okay, so really, in terms of logic itself, every argument looks like this. You got a bunch of hypotheses for H for hypothesis, and then you're using that to show that your conclusion is true, and there's an implication going on. You're like, okay, if all of these are true, then that's what implication gives you, then C is true, my conclusion. Okay, so the process of showing that your argument is valid, that is what a proof is. That's all it is. You have an argument, you show that it's valid, you have proven that thing. Okay, so a lot of new terms, but they are hopefully not too bad. Okay, and this is actually a true statement. It follows from a certain rule that we'll learn about later. Okay, so here is our first real proof using logic. Aren't you excited? P and Q could be everything, anything possibly. So we're not saying what they are, so they could be anything. They could be any of our like little predicates that we've had with particular values plugged in. Okay? Are you ready? We're going to prove the following argument is valid using a truth table. So I'm going to assume the following. Assume that not P implies Q is true. Not of all of that. It's not true that P implies Q. And then let's assume that Q implies P. So if Q is true, then P is true. But it's not true that if P is true, then Q is true. So we're somehow going to prove that not Q holds. Okay, it must be the case that not Q is true. Are you ready? So we're just going to use a really giant truth table to prove this. And let's get started. So feel free to fast forward. I'm just going to fill out a truth table. So we got your true, 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 false, false, true, false, false. That's P and Q. Now let us do the hypotheses. Dun, dun, dun. We have not P implies Q. I'm just going to do them all here. And then we have Q implies P. Dun, dun, dun. So P implies Q in this case is true, but not it is false. P implies Q in this case is false, but not it is true. And then the rest of these, P implies Q for false and true, that's true because the original thing was false. And so negating that is false, negating that is false. So that's not P implies Q. And then let's do Q implies P. So true implies true, that's true. False implies true, well, false implies anything. That's true. True implies false. That's the one case where implication gives us a false. We got cheated out of our conclusion. And then false implies false. That is a true statement because we didn't uphold our end of the bargain. Okay, so these are our two hypotheses. We now need to go and prove that not Q is our conclusion, and this argument involving this conclusion is valid. Okay, so not Q, it's just using Q only, so this is false, this is true, this is false, and this is true. Okay, so do not be scared that it's not like a tautology. We only want validity. So an argument is valid if the conclusion is true whenever the hypotheses are all true, because we're assuming these things and we're using them to prove this. Okay, so let's figure this out. Does it work? Does it work? We're going to find the cases of this truth table where the hypotheses are all true. Dun, dun, dun. Not that one. Not that one. Not that one. Ooh, but this one. Hypotheses are both true in this case. All right. We want to show that the conclusion is true. Is that the case? Yes, it is. I'm going to circle this in rainbow because it's a good day for us. We just proved this. This is a valid argument, so it checks out. We're okay with this. It is a true statement. This is a correct proof. All right? It's true that whenever this is true and this is true, see, that the conclusion is also true. And that's what it means to prove something. Okay? So that's fun, I hope. It's exciting to like actually stick real things in for P and Q, but to prove it logically like this. And you now know without beyond a shadow of a doubt, like assuming these things, this following thing is true. It's so cool to think about. Okay, so now I want you to do it yourself. use a truth table to prove that the following argument is valid. Okay, that this proof is correct. Okay, so hopefully you've tried it yourself. Again, I wonder if I can copy a lot of this, because that would save me some time. Boop. So at least take y'all right there. No, that's not happy. Oh, but there it's happy. I'm very confused. Yes, 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 I'll take it. I'll take that much. Yeah. There's P and Q. Then we'll do the rest. We do the first hypothesis. Hey, go away. P if and only if Q. And P or Q. And then we have to find the cases where those are true and then show that P is also true. All right, P if and only if Q. So this is true when they match up. So true and true, those match. Doesn't match, doesn't match, matches. Okay, P or Q is true when any of them are true. So there's true, there is true, there is true, there is false. And now, P, well, I mean, it's over here, but I'm gonna put it here anyway. True, true, false, false. Because why not? That's our conclusion. It should be on the right. Okay, so we just have to find the cases because we're trying to assume that these things are true. So the cases where they are true is where we want to show that our conclusion holds. So it's only that one. The rest of these have a false somewhere. And what do you know? It's a valid argument. P happens to be true in the case where the two hypotheses are true. Okay, so this checks out. It's a valid argument. We have proven this. No matter what P is, no matter what Q is, this argument holds. Okay, it's always true that if you know that P if and only if Q is true, and if you know that P or Q is true, then P must be true. And you can kind of work this out in your mind as well. It's like, okay, I know that P and Q match. That's what this says. And I know that P or Q is true. And so you can just use process of elimination knowing that, okay, they match. It's true, which means one of them must be true. That means they're both true given this thing. But, I mean, a truth table is a lot more convincing probably. Okay, so that's why it's true, and that is beautiful. So those are two proofs. That's two examples of using logical reasoning. Okay, and I'm sure you hate using truth tables to do this by now. Okay, nobody wants to use truth tables all the time to prove things, especially when you have a ton of propositional variables, like more than just P and Q, because then it blows up exponentially. We don't like that. So some smart people found some patterns like these, and they just wrote them down because it works for any P, for any Q, because we didn't say exactly what they are. It just works always. We tried all the possibilities. It's quite nice. So some people wrote them down for us, and these are called rules of inference. Okay, and there's a large table on the next slide, and we can use these in our own proofs. Okay, if we have some hypotheses, like if we have these hypotheses, we immediately know that this is true. If we have these hypotheses, we immediately know, oh, sorry, if we have just this hypothesis, we know that this is immediately true. So if we have these, this is automatically true. It's been proven already. And now this thing is another thing in our arsenal that we can use to prove whatever our final statement, our final conclusion was. So this is an important one. It's called modus ponens. It's saying that if you have, if you know that if P then Q, and you have P, then you know that Q is true. That's Latin for mode that affirms, because you're proving a truth statement. You're proving that Q is true. And then you have on the flip side modus tollens, where you have, okay, P implies Q, and I know that not Q is true. Oh, that must mean that not P is true. Okay, this is denying the fact that P is true. Okay, it's saying that not P is true. It's proving that. Proving not P. And the rest of these, they kind of go hand in hand. This is saying if you have one thing, if you know just P is true, then you can like muddy the waters and say, oh yeah, then P or Q must be true. And that should make sense without even using a truth table. And then P and Q is how you can break up. Hey, I know that P and Q is true. I know that this is the case. This is one of my hypotheses. And I can break out a P from it because I know that both of those must have been true in order for the whole thing to be true, right? Just look at your truth tables. again, conjunction. If I know both P and I know Q some other way, like I prove these separately, then I immediately know that P and Q is true. Okay, so they're not too bad. If I know P implies Q and Q implies R, I can like put them next to each other. Like I can line them up. And now I know that P implies R. And the rest of these I'll let you look at on your own time, but they're all useful, okay? They were worth writing down. So let's prove to ourselves that modus ponens is true using a truth table, because modus ponens is going to be one that we're going to use quite a bit in our careers, in the rest of this class at least. So modus ponens, it's assume the following. It's assuming that we know P, it's assuming that we know P implies Q. And we'd like to show that therefore Q must be true. Okay? And we can prove this using a truth table. So again, PQ, P implies Q, and for good measure, I'll copy Q over there just to make it all the same. Okay, P implies Q. We remember this? No, surely I don't. True, false, true, true. And then Q in these cases are true, false, true, false. So if it's the case, we're trying to assume that we're assuming that P is true and P implies Q is true, and we're trying to use that to prove that Q is true. Okay, so we've got to pick the cases where those are true. We've got some trues there, and the rest of these don't work. Okay, so this is the only case where P is true and P implies Q is also true. And so we're trying to use those hypotheses to prove that Q is always true in that case, and hey, it is. Okay, so we are happy. We have just proven modus ponens, and so now whenever we see in our hypotheses P and P implies Q, we immediately know Q is true. We can add that to our set of hypotheses. That's the idea. Okay? That's exactly what we want. So, a very nice example now. Let's see how much we have left here. A very nice example is this one. So I want you to maybe think about this yourself. It's not an in-class example yet, but it would help you to do it twice, because I do have another example here. So what we're going to do is try and prove this. You can put the line, you don't need the line. We're going to use rules of inference and the laws of propositional logic. We're not going to use a truth table, because that would take 2, 4, 8 lines. That would suck, 8 columns. We're going to prove that this argument is valid. Whenever you know that P implies Q and Q implies R and not R, that must mean that not P is true. Okay? So we're going to use our rules of inference and the laws of propositional logic to prove this thing. So here's how you do it. We need to use our hypotheses and these laws to come up with, eventually, not P. We have to prove only true things, and we can use these to prove those true things. Okay? So it takes some practice knowing where to start, but just look for patterns. And I see these two together. That is one of the patterns. It's when you can stitch them together. So I can use hypothetical syllogism, which is just a large word, to prove that P implies R is true. Okay, so these are my hypotheses. I am next going to show that, so starting from those hypotheses, P implies R is true, and the reason is hypothetical syllogism. Because I know I get to assume these things. Okay? Dun dun dun. Usually, if you want to be real fancy, you put your hypotheses that you're using to prove these things up above. Like, okay, I'm using this. It's a hypothesis by assumption. That's one way to say it. I'm using Q implies R. That's a hypothesis. That's another way to say it. And then I can get so far, I can get to, let me put lines in between here because that's what they do as well. I can use this one, these two, to prove this by hypothetical syllogism. That's the name of the game. Okay, and then, once I have that, I would like to prove eventually not P, hopefully using this. And if you can take a second, please maybe look at this and see if you can find a rule that can give you that. It's this one up here, isn't it? Modus tollens. So, let's use modus tollens now. We can use not R, that's a hypothesis. I'll just say hype. And then, because I have not R and P implies R, by modus tollens, here's my, just pretend Q is R, P implies R, not R, I have not P. Cool, huh? And of course you can do this in a truth table to just prove to yourself that it works, but this is how you normally will prove things in your daily life. So we have not P, this is modus tollens. So that's how you use things, use your assumptions to prove new things to eventually prove your conclusion. Okay, and that's a proof. It's really not that bad. It's just a lot of pattern recognition. And you're getting good at that because you're a computer scientist, right? You've had enough experience with that in your programming. Okay, so I think that's where I want to stop. We'll come back and warm up with this example next time, and then we'll start learning how to prove things with quantifiers included now. So no more hand waving. It'll be very exciting. So yeah, those are my plans, and I will see you in the next lecture.